So we've got two kind of completely different lectures today that happen to fit into the same structure. One is looking at kind of Gestalt, how we perceive overall viewpoints and particulars, and the second is uncertainty, right? And so how you display uncertainty intentionally when you have that in your data set. So we'll start in with the Gestalt. Before that, as always, some examples. So today we're going to be looking about patterns and how to display things in ways that will let the viewers understand patterns and not do them in a way that will falsely show them patterns that shouldn't be seen. So there's a couple things. One is to kind of identify known patterns, and the other is to learn things new about the data that you weren't expecting. And that is kind of one of the key reasons for visualization, is to find things you didn't know you were looking for. If you knew exactly what you were looking for, statistics is often the tool you want to use. If you don't, then visualization is often the tool you want to use. So we're going to look at how do you kind of see things in a group, what are visual characteristics about that, how's 2D space divided into regions, when are patterns seem to be similar, and when do different display elements appear to be related, and kind of how the different tools you can use to do that. For each one of those, I'm going to try to show a kind of a design example of when you would use this or when you wouldn't use that, except for the ones where it's completely obvious. All right, so we talked before about the kind of parallel, fast, pre-attentive extraction of features, form, motion, texture, color, even stereo depth, that happens down early in the visual system. We're going to talk in a later lecture about kind of large, kind of how do we group objects into scenes and coordinate things that way, and kind of working memory. Today, we're going to look at pattern perception. This actually happens kind of in between these two states. And it turns out that we want to understand how to organize data on the screen, so this is how structures will be perceived. And so the kind of bottom-up parallel processing meets the stage one intentional processing here. And of course, there's feedback, right? And so basically, when we looked at the video of the gorilla, right, if you were looking for white-shirted players doing passes, you didn't see the gorilla. If you were looking for dark-shirted passes, you would see the gorilla. And so kind of which things you pull out of that sea of kind of parallel information can be tuned by what you're intentionally looking for. And so we're going to take advantage of that in the visualization. All right. So we're going to look at basically these Gestalt rules. And Gestalt is kind of a German word that there is no English equivalent for. It's kind of a pattern. And so it was a school. And so basically the actual mechanisms inside the brain that this school proposed that we do these things, almost none of those held up, but the actual kind of behaviors all have held up and are kind of a good way to think about how people perceive things. And so there are a bunch of different rules that they talked about. Some of them were stronger cues than others, and so there's kind of an ordering to these cues. Proximity, symmetry, continuity, and closure were the stronger ones. Similarity, relative size, figure, and ground are kind of not as strong. And so when we think about how do we want to display things, we want to use the strongest cues for the most important characteristics that we want to show in the visualization. And so proximity is one of the strongest cues. And so basically things that are close together are perceptually grouped together. And so we see three vertical lines of dots on the left, three horizontal dots on the right, and two groupings on the right side because they're closer to each other than to other things in the scene. It's an interesting question here. Which group do these two orange dots belong to, right? Because it turns out that they're completely reasonable bounding with either the left group or the right group. They're the same density as either of those groups. I tend to see them as the ones on the left, maybe because closer is better, even when you have kind of uniform density. All right, so the design principle, of course, is place related elements nearby. And this is used, for example, in multidimensional scaling. When they take points from a high-dimensional space and project out into 2D or 3D, you can actually use spring forces to cause the ones that are close in high-dimensional space to be close in two-dimensional space, and you can get clustering grouping information along with that. A lot of these techniques will be more useful in information visualization than scientific visualization because we already have a spatial embedding, but that would be useful in a couple of designs in the class already. All right, so symmetry. So basically bilateral symmetry is stronger than parallelism. And so this looks more like, and this looks more like than this does, right? They tend to group together. We see a kind of a symmetric object rather than parallel objects. And symmetric shapes are seen as more likely, right? So this picture on the left could be this shape behind this shape. but we don't perceive it as such. We perceive it as a cross in front of kind of a uniform white square because those two objects will be more symmetric than these two objects. And so we just have this kind of assumption of symmetry. And so this can be useful to advantage because you can include parts of things that are symmetric, and the inclusion doesn't bother the visual system because we're assuming that it's symmetric to begin with. All right, so the design principle of this, yep.
I didn't quite get what you meant by that. If you include things that are symmetric.
So if these are your objects, you're going to fool the user with occlusion. If it's really kind of a plus sign and a rectangle, if you had an occluder kind of covering part of the rectangle, it wouldn't be such a problem because we're going to perceive it as a rectangle to begin with. So we're kind of expecting symmetric shapes.
Do we have a tendency to make almost symmetric things look symmetric too?
I don't know the answer to that particular question. We certainly see symmetry in almost symmetric things. Whether we'd be able to perceive that they weren't quite symmetric, I think you can, because faces are this way, right? And so you'll notice that someone has an asymmetry in their face very clearly, but you'll still perceive it as a mostly symmetric face.
Well, if you see a mirror image of their face, it'll look totally different. So we're sensitive to the
polarity of the
delta asymmetries, I guess. Yeah.
All right, so this is the slide particularly for the group that's looking at time series, right? So if you're trying to compare two different series together and you want to see where they're correlated, or also perhaps for the protein data sets, you can do this trick of showing one on the left, one on the right. So this is an interface where you would slide the left one up and down until you saw the symmetries. And then it would kind of very, very rapidly be able to survey a whole bunch of different hypotheses to see which are the most likely alignments of these two different signals. All right, so continuity, we expect objects to be continuous. And so again, the question is which shape is this? And we expect it to be the middle shape, not the right shape, because these are kind of more continuous curves, and this has got these two kind of catastrophic discontinuities. So when you're drawing these kind of node graph diagrams, it turns out that putting sharp kinks in the edges makes us confuse those with all the other crossings in the scene. And if you turn them into kind of smoothly varying things, now the crossings pull out very distinctly from the kind of right angle changes, and you can more easily trace through figures these things. Harder to compute, but much easier to comprehend when it's drawn this way. So connectedness. And so here, even if objects are different colors, even if they're different sizes, even if they're farther away from each other, if they're connected, it kind of overrides the other ideas.
If you go back to the previous slide, like
yeah.
it showed like smoothness is better than that, but we see that in circuit diagrams you use that the second part, right?
Yeah. So there's two bad things about that. One is if you're a person trying to understand it, you're going to have a hard time. The second is there's actually more resistance at those corners than there is at curvilinear things as the electrons go through there. So it turns out to be bad for a couple of reasons. It's just that was how the CAD tools were designed to lay things out earlier. You also have the benefit that you don't have to wonder about the spline interpolation and how close are these two things ever to each other. So there's kind of reasons for laying it out that way, but they aren't because it makes it easier to perceive.
If you look at old PCBs that were laid out by hand with tape, all the traces are curved, and they're much easier to follow visually. They're also bigger, which helps you.
All right, so here there's positive and negative design statements, right? And so you can connect two objects to group them, even if they're kind of for other reasons separate in the scene or different colored or so forth, but don't connect them or they'll appear to be grouped no matter what you tell the user about different colors, right? So again, a closed contour is seen as an object, and our perceptual system closes gaps, right? So we perceive this as a ring behind a box, not this kind of half Pac-Man shadow figure coming down and barely touching. So contours separate the world into inside and outside the contours. This is why Venn diagrams are so powerful at showing set relationships. Here, both closure and continuity help. And so I was talking before about being able to occlude some things. If the thing that you're occluding is symmetric, it's going to be perceived as symmetric anyway. And so this is one of the reasons we have windows on tops of windows, and it works fairly okay. You can understand which things are on top of which and see them as groupings. For symmetric objects, you can get away with some of that. Now, the other thing that happens is these closed rectangles provide reference frames for motion, and we're going to see that later in the motion section. And so things are kind of, described with respect to that frame. You can move the whole frame with the objects inside and around, and you don't perceive this kind of, peculiar motion of the objects inside. And so similarity. Here, color and shape can group things by row, and those are basically separable dimensions. And so here we've got color by one row and then kind of horizontal and vertical by the other, so you can decide to kind of look at that as rows or look at it as columns. Here there's integral dimensions, so it's two kind of width and height which form together into shape dimension. And so it looks more like a kind of a herringbone shape where there's these thin things with larger things in between them, and it doesn't look like two rows, kind of a rows and columns things done by kind of width and done by height. So you should have similar characteristics. This is kind of an obvious one for objects that you want to group together. Relative size. So the smaller components of a pattern tend to be perceived as the foreground and the larger parts as the background. So this is a black propeller kind of on a white background, not a white propeller on a black background. Horizontal and vertical things are special. They tend to be viewed as objects. The ground and trees, I guess, and people walking around are this way. And this plays into figure ground. So you want to make dots the object, not the cheese grater, right? And so that'll be a bit easier to perceive, more naturally perceived by the viewer.
But that looks like as a center because that has a different color and it's accentuated because of the illumination.
Yeah, it used to be, when I did this talk before, there used to actually be a connection between the black dots and the propeller. So I put the blue dot there to look through the background. There's a complex relationship with figure ground, and you're right, it's not always as simple as, okay, that's going on, because this color is kind of brighter than the propeller, so you might think it's background as well. The idea here was you're looking through the whole shape to a blue background, but and still you get kind of larger objects to that.
Can you explain that design principle again? I'm not sure what you mean by cheese grater.
All right, so if you have a cheese grater, it's basically a bunch of metal with many holes in it. And if you show that to the viewer in this way, they're going to perceive this as a bunch of dots more than a cheese grater, right? And so you want to think about, how do I display my data as the small things that are in the foreground as the object rather than the background? Unless, of course, you have a cheese grater to show them. You want to think about, how do I move things so that it's obvious that they're all together? All right. So the fundamental perceptual act in the Gestalt school is separating the figure from the ground. And so all these perceptual rules are kind of understand to group objects, and we say, okay, these are the objects against some background. And so, what's foreground, what is background, and all the other principles determine that. So on the right side, we have a little bit of a challenge, right? On the left side, it's easier. It's a small object, it's symmetric, and so it looks like there's one figure in the center and the background is around. On the right, we've got ambiguous cues, right? So there's about the same size of dark and light area. Symmetry holds either way. There's a contour around the frame, and so you could have the objects, the contour be part of the figure or part of the ground. And so essentially you can see that as a vase, or you can see that as two faces looking at each other, right? And you can actually kind of jump back and forth between those two with attention, and there's no strong cue for which is which.
You can't see both at the same time.
But you can't see both at the same time, right? All right, and so this is like the only time in my life I've ever gotten spam, and it's been useful to me. Right? So somebody sent me a bunch of these kind of figure ground illusion pictures. And so on the top, you're basically transitioning from, it's obviously a colonnade is the figure, to in the front, the ships are obviously the figure, and in the middle, it just gets weird, right? And on the right side, it's kind of a waterfall coming down a canyon, and at the bottom, it's people kind of walking and touching the wall, and in the middle, again, it gets very strange. And on the left, it depends on how close you are to this, kind of which comes from me. What I see from here is a man here with kind of a beehive on his head, another one playing a guitar, and a lady coming out of a doorway. But from further back, it's two old people, a man and a woman facing each other, and this is the old man's ear. And again, it's playing with
Oh.
these different principles to show you that, you can look at the figure and ground backwards and you get a completely different answer to what's going on.
Now I see the dude in the hat.
I don't know what the heck the lighting thing is behind them, but it's kind of a chalice, right? You can view this as a chalice as well in the middle of other things. So there's three, kind of things playing together in that visual.
Oh, that is really creepy, Russ.
All right, so contours. There's perceptual contours that are boundary between inside an object and outside an object, between two objects, between foreground and background. Lines, basically sharp changes on both sides of intensity can be a good boundary. Different colors can be boundaries. Two different stereoscopic depths can be boundaries. You can actually get depth from blurring, right? So it turns out if you're looking at a person's head against a background, if you're looking at the person's head, their contour is in sharp focus and the background is blurry. If you're looking at an object that's in front and out of focus, the boundary is blurry. And so whether the boundary is blurry or not tells you whether that's the kind of nearer object or the farther object. Stereo discontinuities can happen there as well in texture. But there are also illusionary contours, right? And so what that means is that there looks, when you look at this picture, you perceive a contour that goes all the way around as if there's this white shape in front of all these other behaviors. And it turns out that there's neurons in your brain telling you, yes, there is a contour here, right? So it's not just, you think, okay, let me imagine it. No, there's neurons that are kind of saying, okay, I see a contour here, it's going out, I'm going to excite some contour, neurons out this way. This one's exciting some contour neurons perpendicular, and those flow together and form a perceptual contour, even when there's no image-based contour. So computer algorithm has a hard time because it just says all the pixels are the same. We have an easier time because it's actually forcing these contours in there. All right, so when do contours jump gaps? And so basically, if there's a consistent path between them, even if this weren't drawn here, this is drawn here, you're not having neurons tell you this, you would perceive a path that goes continuously through those. Whereas these two don't have a consistent path, it would have to be kind of a large, discontinuity. And so you get a perceived contour through here. And this explains why this arrow alignment, head to tail, works so much better than kind of a grid-based alignment, because there's not a good continuity between these arrows, but there is between these arrows, right? And so you kind of perceive breaks in the flow and strange things happening here that aren't necessarily present in that. And so you want to line up things to be able to jump gaps. And I think I sent the email of the pair view trick for doing this. If I didn't, somebody shoot me an email, I'll do that, which is basically you extract streamlines and then you subsample the streamlines and you do another little streamline and an arrowhead to get arrowheads lined up front to tail in those displays. So edge completion, right? So again, here we're seeing not four Pac-Men kind of getting ready to gobble each other, but four white discs with a square in front, and we really see a contour here. And you might say, okay, well, it's a light-dark contour, that's what's going on. But no, if you make it a dark-light contour and a light-dark contour, we still see it as kind of a gray square in front of these things. So it isn't the case that like black and gray spread out in here, and that white and gray spread. It's really the case that contourness spreads out into the gap from both sides, and you kind of got a contour closure going on. So contour extraction is something that's happening very deeply in our visual system and is important to understanding objects. You can see why that would be.
Does it have a higher is it stronger tendency if it's a straight line versus a curved line?
It's a stronger tendency if it's a smooth line and if it lines up across the gap. All right, so we saw before this, where there were curved lines, and as long as there was good contrast and good continuity, we saw the shape continue.
So it's proximity of the, if you spread that out a whole lot, it might.
Then it'll break.
But if you made that a circle with squares in the background, you'd probably see the same thing.
All right.
Think so?
Yep. Transparency. So this is trying to show multiple layers. There's many potential pitfalls. I always think about the Lost in Space episode where the robot would run around right before it's getting attacked. Danger, danger, warning, Will Robinson. And so basically different layers can interfere with each other to some extent. And so sometimes they'll fuse perceptually into one other layer that doesn't look like transparency at all. Patterns that are similar in color, frequency, and motion, or so forth, can interfere more. This is what we saw with Vicky and Tronte's study of vector field displays. 2 texture patterns interfered more than a texture and a line pattern. 2 kind of glyph patterns interfered more than a line and a glyph pattern because they were similar. And so you want to make layers differ in at least one significant dimension and then try it out to make sure that it actually works the way you're hoping. And so you basically need good continuity and correct color relationship, right? So it looks here like this object is going behind a darker screen because the color makes sense for it and there's good continuity, whereas down here it doesn't look like it's transparent anymore because there's not good continuity going on. So this looks like, kind of a strong pattern in front of a lighter background pattern. The transparency works pretty well. This works fairly reasonably well, right? So you got 2 different ones going past each other. This, you've got a problem, right? They basically have lined up with each other, and so you don't see any transparency. Here we have another problem, that these are not really separable, right? Because we end up seeing a region of plus signs with a region of dashes and a region of horizontals, rather than kind of a transparent thing. Although, if we think about it, we can say, oh yeah, this is really transparent and seeing that same thing through.
And the only one of those where you can sort of clearly say which one is in front is A, right?
Right, it's the only one we clearly, right, you can't clearly say which one is front there because they're the same either way. Yep. All right, so this slide basically ends up in this talk because there wasn't another good place for it. The idea here is people have been studying maps for a long time. They've got a really good visual grammar for how that works. So if you can reduce your visualization problem to a map problem, you're probably going to do well by just stealing all the tools they use to show maps, right? And so there's basically closed contours to show geographical regions, or colored regions to show geographical regions, and then you can lay these over top of each other to have one kind of regions as lines, one kind of regions as colors. You can also do texture regions, right? So the swamps will be this way, or the trees will be this way. So now we're getting a large number of ways to show regions. If you try to overlap all 3 of those, you might get into some trouble, but this gives you certainly a nesting way to show different shapes. Lines are linear map features. Dots are different things at scale, right? If you zoom way out, they might be points. If you zoom way in, they may be restaurants, right? And so they're kind of showing some compact region. This is, the thing is on the road, the thing is on the river. This is inside the region, and so forth. All right, so here we've got overlapping color and contour and texture regions to show, which of these 3 things, that the lake is inside the county, which is inside the watershed of, something else.
If we have overlapping contours, it is necessary that each of those contours have a different texture, right, to easily discern.
Well, if they have good continuity and they don't have good continuity except for one way, they wouldn't be so ambiguous, right? So if you had small round regions against kind of large square background regions, I don't think that you would have a confusion over the crossing. If they were all curvy regions and they came across each other, then yes, you're going to have a misunderstanding of which line goes to which line.
But if the contours are of the same shape, then the only easy way to make out like 2 contours would be if they have a different texture.
That's right. You could do a different texture in the internal region. You could do a different line style, which may be what you mean by texture, like a dot dash versus a continuous line. Or you could do different color inside outside for the lines. Yeah. Certainly for the roads, you'd have to consider kind of a line style because you don't have an inside boundary to draw that. All right. So form and contour and motion. It turns out that contours of regions can be seen by motion alone. And so it can be seen as well as if you drew the contour where it was. And it turns out that phase of the motion seems to be the most relevant. So if you have different amplitude motions of objects, those don't tend to group together. But if they move in phase, then they do tend to be grouped together. And so let's have a look at that. This is one where I emailed Colin asking him, do you have an example of this? And he sent me a little app. All right. So here we've got several groups of points. It's a little hard to tell which of these points belong to which cluster in here. If we start moving them in phase, now we can start to see the ones that are moving in phase are grouped together. We have two directions of phase, and now we even have a better understanding kind of which of these things are moving. You can do a similar thing with color, right? And so we can disambiguate by phase motion, by color. We have multiple colors that we can use to try to separate these. And so here we've got kind of the maximal separation in the colors by a separate nominal coloring, as well as the phase, two-directional phase mapping. And then back to the original. And we can see a stark difference between those two. All right. And so you should think about, as you're doing animations, maybe if you have these points, it's a good way to disambiguate clustering. It actually works great for the data-driven spots, and we saw that in one of the videos there. Even linear motion kind of pulls out the ones that are moving in common direction, and you can see the flickering in the same phase showing what's going on. All right, so as I mentioned before, rectangular frames can form a strong background within which action can happen. And so if you have a frame that's kind of moving to the right and a dot that's moving to the left, you end up seeing basically a stationary dot in a moving frame looks like a moving dot, right? Because you follow the frame back and forth, and it seems like the dot's moving, not the frame moving. When a group of dots moves like this, it's perceived as a group of dots moving right and left together with one in the middle moving up and down, rather than kind of three separate motions of those dots, assuming that they're in phase with each other. All right, so motion design principles. It can be a strong cue for grouping. You want to add a frame around the related particles to form the context to show the relative motions. And the speed should be about a few centimeters per second, right? And so if things are too slow, it turns out to be challenging to follow them based on just memory. How do I do this? Here we go. All right, so here's a moving bead. It's actually a polystyrene bead on which they've placed a protein that causes actin to polymerize. And so it builds a little scaffolding, and then it pushes the bead along a little ways. And so if we do
Make it bigger?
this, I might be able to make it bigger. I have to make it bigger without showing the other half of the picture.
Oh.
And so it builds a little scaffolding, the bead gets pushed a little bit out of the way, and then it builds another scaffolding, pushed it out of the way. This is how bacteria jet around inside your cells. How exciting. And so this is that same protein attached to a bead. And so the question is kind of remember what the path was that this thing took. Is it turning towards the right? Is it turning towards the left? It's really challenging to see at this speed. But if we set it in motion, we get kind of a good streak memory of what's going on, right? And so the speed of motion turns out to be important. And this was actually, they fluorescently labeled the bead, but a second fluorophore labels the actin skeleton that's behind it. And so this is showing literally the stuff left behind as the thing was jetting around inside the frog egg extract, I think. All right. So if things are too slow, you actually want to speed them up. I was just recently looking at this with some video data I got from a blood clotting study. And the question was, what's going on over time with these posts that are moving? Are they sticking down? Are they staying up? And if you watch like every frame, maybe one will change, maybe two will change. If you go quickly through the video, you see them all collapsing as a group. And frame to frame, you have a hard time catching this, but over time you can see the motion once it's sped up. All right, this is the other direction, right? So this is going at 30 frames per second. And your cilia beating inside a human lung cell culture. And so these are basically a bead attached to a cilium, and the cilium beat about 60 frames per second, about 30 frames per second, right? And so basically understanding the motion of this is just too fast for us to perceive. And so what you can do instead is take the data, slow it down some. And so here's kind of an XY plot, a YZ plot, and a 3D track of where this bead went over time. And you get a better idea of the overall trajectory. It also helps it leaving its trace behind, so you don't have to remember where the bead was. And then this is just showing the speed. So it goes faster forward and slower backwards, faster forward, slower backward. It's kind of like asymmetric rowing action that the cilia do to move the mucus up out of your lungs.
Huh.
Not too fast, not too slow, just right. So motion can also basically express causality. And so if you have one thing come up, hit another, and the other one moves, you see that you perceive this as launching, right? If it hits and a little while later it goes, you kind of perceive that still as launching. If it hits and it goes 10 times as fast, it's like triggering, right? This triggered the catapult to shoot the thing, or the mouse triggered the mousetrap. It turns out that if you have motion, if you just put me in a dark room and you put lights on my joints and I move around, you have no problem understanding that as a person, right? Just seeing these dots of light move in a consistent way with the way a person moves. And it turns out that motion patterns can express behavior, right? You can imagine the happy triangle comes up to the excited square, and he tells them about the sad circle who's had a bad day. And so you can express things beyond information, some emotional content in motion that's potentially useful in your display. All right. So now we've gone from Gestalt through motion and look at visualizing uncertainty. And so a lot of the visualizations that you see, the underlying data set is uncertain, but when you see the visualization, it's drawn an isosurface and the exact value, where it looks completely certain. And so that's a little bit of a problem, and it's a problem kind of across visualization. So people have started to study this question and ask, okay, how can we portray not just the kind of expected value or the most likely value, but also the range of possible values that are out there, so that the scientist or the surgeon will know kind of how much to trust the visualization and where they can't. So this is kind of like where are the error bars, right? So if you show a plot in a research group, they're going to ask you where are the error bars. In the visualization, you get the same question. All right. And so we can think about where are the sources of uncertainty. One is in the actual detector itself, right? Or the numerical simulation, there can be error in the measurements, right? And so we see this with the cores through the ocean, right? There's different thicknesses over time in different locations. The shift then is not exactly known, so they say, here's our best guess, but we know it's distorted by things, some of which we know, some of which we don't know. So the original measurement can actually have distortion in it, and certainly will have limited bandwidth. And so if you take a picture with a camera, it's an 8-bit camera, you have 255 levels of gray, and that's all you get. If it gets too much brighter than that, it saturates, and even in between, you only have a certain number of levels of intensity difference you can detect. Then you transform that, maybe from kind of a grid longitude latitude into a sphere, and you can have some small transformations in there. In particular, if you're looking at a kind of a place on the data values that is not in the sample grid, right? You're doing some interpolation, right? So you've got these measurements, and you draw a line, right? Or maybe you draw a spline, right? Either of these could be the correct signal that's underneath these. Normally we use linear interpolation, and so there's kind of known discontinuities and interpolation error, but any interpolation you do, unless you had band limited the signal on the way in, you're going to have interpolation errors. If you band limited the signal, then in fact Nyquist tells us you can get away with showing actually all the information that's in the signal. And then there's the visualization, right? And so we do a color map, right? And we know that if you do the grayscale color map, there's a 20% average error in perceiving what's going on there. Even if there was not an error, there's kind of a discretization in a certain number of color levels in the display itself and a certain number of pixels. All right, so how do you kind of combine all these and then show the resulting thing? So this is a taxonomy of uncertainty that goes beyond this, that says, okay, sometimes you've got people that are getting information and the information is intentionally wrong, right? They're trying to fool you into doing something. That's a different kind of uncertainty. Sometimes it's an unknown description of what's going on. Sometimes it's undecidable. You can't tell. Mostly, this is a useful way to think about these. But in the end, most of the visualization techniques I'm going to talk about are going to boil down to if you can give me a numerical description of the uncertainty, then we can do something in our display techniques. All right. And so there's a question about error bars versus ambiguation, right? So there's a difference between statistical uncertainty and bounded uncertainty. Statistical uncertainty is if you take a bunch of measurements of something, often it'll have a normal distribution around the actual values. What that means is it's incredibly unlikely but possible to get a value very, very far from the actual one, but much more likely to get one that's close. On the other hand, if you had quantization error from your camera, what you have is basically bounded uncertainty. I know the brightness of this pixel was between this and this, but anywhere in there would be represented by the same thing in this 8 bits, right? There's only 256 levels you can have, and so even if there's no noise, you still have uncertainty on this interval here, right? So one kind is bounded. There's no particular, favorite place. It's in here somewhere, and the other is statistical. And so this approach here is to use ambiguation for bounded uncertainty, and so this is literally error bars, right? And so it could be somewhere between here and there, right? And so this is showing, here's the line, but here's plus or minus where it might be. Here's the lower part and upper part for where it might be. Here's the range that they could be in for a scatter plot. Now, these error bars are often used to show statistical uncertainty, and then what you basically have to do is pick some probability and draw the lines there. And often what's drawn is standard error, which is the standard deviation divided by the square root of the number of samples, right, or minus 1. And this gives you kind of a range of the likelihood of it being. So here's an ambiguated line chart, right? So the values are somewhere between the top and the bottom of this chart. They could be anywhere in there. An ambiguous pie chart, an ambiguous stack bar chart as well. All right, so there's kind of 3 ways you can think about uncertainty. One is it's just another scalar field, right? I've got my scalar field and I've got my uncertainty, which is another scalar field. So I'm going to do a multivariate visualization, and I'm going to do the height from data and the color from uncertainty. Or maybe the height from uncertainty and the color from data. And so you can treat it as another data set to layer on top. The second one is uncertain data may take on a range of values, and then I want to show this range of values, right? This is the ambiguation. Here's kind of the top and the bottom where we might have this data set. And the third is uncertain data shouldn't be clear, right? The less sure we are about it, the less perceivable it should be to the viewer. And so we're going to actively prevent users from making judgments based on this data. We're going to make it so that they can't tell what's going on, right? And this kind of makes the verisimilitude match the veracity, right? You can't misinterpret it because you can't interpret it. All right. There's also 2 classes of visualization techniques for visualization. They kind of match these different approaches. Extrinsic basically says we're going to add on another technique to show the uncertainty. We're treating it as a different data set. I'm going to display it that way. And the other is intrinsic, which is we're going to vary the properties themselves. And this can be used both for either kind of second view or the third view, which says we're going to, in the display techniques, vary things to see what's going on. Transparency we talked about before, right? The more transparent it is, the harder it is to perceive. So that's one good use for uniform transparency. All right, so this is looking at fuzzy classifications for multispectral imagery. And so basically, there's kind of a thick line where we think the average is. Then there's kind of the first level of uncertainty, the second level, and the third level. And so you kind of get less and less likely to less and less contours as you go away from the actual data itself. The mean reflectivity, is shown as the dark line here. This is a technique that's basically using extrinsic display. So this is got all kinds of rainbows on it, but this is a 2D display that's showing the remote sensing information. And then along these walls, we're seeing the uncertainty. But we're not just seeing, so that we're basically seeing along this line is what's along this blue line. And along this line at the middle of the page is kind of this point, right? So this is all the data values, the density of data values at that point. And so in other words, there's a probability distribution that in this case is bimodal. Some of the values are down here, some of the values are up here, so a mean wouldn't very well characterize what the possibilities are. It might be this or it might be this, and it's about equally, and they're pretty far from each other. Whereas over here, it's unimodal. Like there's one peak, this behaves more like a standard deviation. This is where it is, plus or minus some value. Here, you can't even say plus or minus some value. It's like, no, it's a bimodal distribution. So this is trying to show both the whole density distribution along one of these lines, and then the distribution along this line, and you can kind of get kind of a cross-section at the point. And so this is using a height field plus color map to show the uncertainty distribution, and basically a color map on the plane to show the data values.
I think that's horrible.
think the rainbow's horrible, but the idea of using the distribution functions up the side is a very interesting one. All right. Saturation is an indicator of uncertainty, right? And so this is saying, okay, this is the third model, which is where I'm going to make it so you can't tell if you shouldn't be able to tell, because you can't perceive a very low saturation, what the hue of that object is. And so we've got a color wheel that basically shows you very certain values, very uncertain values, and good luck. So this, at least, is showing you, highlighting parts of the domain where we actually have a reasonable estimate of what's going on, and it's naturally fading away the ones where we don't have a good estimate of what's going on. So you don't make any interpretation about these areas because you don't have the data values there.
Best to use isoluminant colors if you're going to do that.
I don't know why you would want isoluminant colors.
Because you're using the desaturation to...
So you're thinking if they're not isoluminant, you have a hard time judging saturation level differently. Yeah, I would believe that.
And they seem to have done that okay, but like
There's
the yellow,
like one
like the
level,
red sticks
two
out more than the
levels,
yellow.
and
Yeah.
none. Yeah.
Yeah.
And so we don't expect to see a lot of different levels on saturation and hue, and we kind of don't get it. And so, yeah. All right, so this is looking at temperature, soil, and precipitation, encoded as red, green, and blue, showing how much each contributes to uncertainty in a water balance model, right? So this is trying to show the uncertainty on kind of a three-dimensional map, and so it gets more saturated to one color if one of the error terms is dominating in a particular location. If you had basically one error term that was bad everywhere, you'd have a red surface there. If you had one error term that was a different one, it would be green everywhere. If there were just two, you would never see any blue. And so this is showing you that there are some blue areas, some green, and some red. So the model, different parts of the model are causing uncertainty in different areas in the domain. You can also use this to make the uncertainty map to the color intensity, which I think they've done here, so that black areas are actually fairly certain, and there's not a lot that you need to worry about. And so if you're looking for how to improve things, you would use this.
Except you can't see how high they are.
The height field is pretty exaggerated.
What's the height field?
I'm going to guess the height field is also the uncertainty, the amount of uncertainty, magnitude.
Where's the data?
We're not seeing the data.
This is just the uncertainty?
This is just a mapping of the uncertainty.
Okay.
Yep. So this is like I'm trying to debug my approach for showing, for simulating things and see where I can do a better job. Yeah, this is kind of an extreme case of extrinsic. We haven't even shown you the data. We've only shown you what we know about the data. All right, so this is trying to understanding isosurface uncertainty, basically using a color map to show uncertainty intrinsically, right? Extrinsically. And so these are the isosurface for different threshold values, right? You can see how much it varies as you vary the threshold just a little bit. And so the areas that vary more are going to have a higher uncertainty in the display. Again, you can use transparency to hide uncertain data, and so this is going to fade the data into the background where we don't strongly know about it. And so at the top, we've got everything the same transparency, and down here we start to fade away as we get uncertainty. This is doing the same thing in volume rendering, right? So here, rather than the transfer function depending so much on the data value itself, the opacity depends on the certainty that you have in the data. And so this kind of gives you regions of where there is high certain data, and the color is telling you what the value is. And so we're basically a transfer function in kind of a transfer function space where this is the data we know about, and this is the data we don't know about. And we can start to see, as we change the opacity function, the more uncertain we are, the less we see what's going on in the data. You can actually use animation to show this. And so basically you can sample from all the different possible data values that are at a location, and you can kind of put them in with the strength of that particular interpretation. And as you cycle them, areas that are pretty consistent will stay the same all the time. They'll be the same value, but ones that might have multiple values will vary a lot, and so they'll be noisier. And so you'll have, again, a harder time interpreting what's going on. And so you're basically going to randomly select based on the probability distribution. If this pixel is 30% forest, 10% desert and 40% ocean, it'll be mostly blue, but sometimes the other colors. Where if it's 100% of desert, it'll just be white the whole time.
And the contour recognition sort of kicks in. You see the
Yeah,
pattern.
and so this is a case where you wouldn't want to kind of have this necessarily side by side because it would be hard to look back and forth. You wouldn't want to interpose something in the frames, but if you just from frame to frame change things, you can see the popping, flickering happening. Similar thing done in 3D, and so this is probabilistic animation and volume rendering. So again, you've got a classification, right? Is this bone? Is this kind of connective tissue? Is this skin? There's regions in here where it could be any of these things, and there's kind of a probability distribution of this. And so you can basically do the same thing where every voxel, you'd use the transfer function associated with, with its likelihood with the relative ratio that it's that material. So it turns from pink to white to blue with the likelihood that it's one of those. Areas that are in here stay blue the whole time, areas that are here stay white the whole time, and in between it's kind of fuzzy changing and gives you an idea of what the relative mixture is.
It can kind of mess with shape, though. I've noticed it in a couple of these examples.
It will definitely mess with shape. You won't be able to tell the shape in areas where you can't tell what the material is. And that could be a good thing, because what means shape if you don't know what the material is you're looking at? All right, so this is kind of going down to one dimension, and back to your point, you can have different line displays. This is saying, okay, the less I know about the line, the less of the line I'm going to draw. And so you kind of get an idea that there's, very clear contours up here and not so much down near the outside.
There's uncertainty in the areas where the spaces are. It's just like
In this
the-
case,
the
no,
more dashed is
it's
more.
uncertainty along the whole line, even the places that are written there. So that's a little bit different than you'd expect, maybe. You think, oh, well, it's really certain at these locations, and yeah. That's not what this is meant to indicate. This is more like that. This is saying, okay, it's a parallel coordinates plot, but we actually have distributions on our estimates of the values that we have at these areas, and the question is, what's going on here, right? And so this is the same data set drawn with and without the uncertainty used to blur each of these lines, right? And so it turns out that there is, in fact, a strong correlation going on between these data sets. You can't see them on the left because there's so many distractors that are just random things that happen to be going whichever way they're going. But in fact, we're fairly uncertain in their position, right? So all the energy that is in here is over here, but it's blurred out when to match the uncertainty. And so you can focus your attention on the things that are more certain. And so this is basically a density plot versus just a line overplotting. Also helps with the overplotting problem. So this is kernel density estimation. So this was doing it with kind of all straight lines. We have the problem we knew before that there's the discontinuities, and so we have a hard time tracing lines through this. You can also use lines that go smoothly through there so you can trace things better. And again, here there's this kind of very interesting cluster going on here. Like, what the heck is going on with this? There's some data we should care about. We can tell where the tumor is in the person's head. No, actually, we don't know anything about that axis anywhere. And so there just happened to be a cluster of things close to each other because of the way that it was sampled. And so, again, this can let you know where to pay attention to things and where not to pay attention to things, rather than showing everything as if it's perfectly well known. You can do the same thing in scatter plots, right? And so here we want to understand what in the world is this thing here. Very interesting, very far from all the rest of the data, very uncertain, right? And so basically that point is spread over the entire range. It could be anywhere in the image, it just happened to land there. If you just do the densities and not the points, you have a hard time perceiving where the data scatter values were. You can actually then mix them back in so that you have a point. The more certain the point, the brighter it is. So this one still doesn't show up. It was very uncertain. And so you get both kind of a mixture of where the actual mean points were, but also what the overall uncertainty is in those points a little bit better. So this is trying to do uncertain region AFM surface reconstructions, right? So an atomic force microscope works by taking this tip and scanning it across the surface, right? But the tip has got a slope to it, And so areas where, you know, it's kind of on the side of the tip here, you don't actually know what the value is, right? You've got to estimate the tip, not the value. Whereas flat areas, you've got a really good estimate of what's going on. And so this is trying to, unfortunately, they used height fields and brightness to do both these things. But the idea is that you do know what's going on at the tops of these things. You don't know what's going on along the sides, and then you wouldn't know on the flat areas again. So you can kind of mark the surface by uncertainty. I wouldn't have chosen this particular technique to show the uncertainty, maybe transparency, maybe color to show that. But interesting idea of kind of knowing where you can believe the data, where you can't. So this is uncertainty in astrophysics data, right? And so here is all these objects that kind of point towards the Earth. Why do they point towards the Earth? Well, because they're in peculiar motion around each other, and this Z motion changed their Doppler shift, and so they look like they're further or nearer. Right? So this is saying for objects that we see that they're in peculiar motion, we actually don't know where they are, kind of in far distance. They could be anywhere in this range. And this freaked out the astronomers when they looked and everything was pointing back at the Earth, and they're like, oh, we are the center of the universe. This is really strange to us. It turns out that, you know, basically that's because that's the direction that Z shifts you in Doppler shift. So this is looking at kind of a hurricane, right? This is, or sorry, in case where will a star be? This is a hurricane. Yeah, so this is using hurricane maps on stars, right? If we don't know which way the star is moving, we have some uncertainty in where it's going to end up, and so it's kind of using these hurricane probability plots to show where the star will be. So here's a bunch of glyphs you might use to do this uncertain velocity, and there's a paper that describes kind of which characteristics they showed effectively and which they didn't, and so you can go look that up and pick your favorite glyph for showing vector field uncertainty. So this is using one of those glyphs to show uncertainty in fluid flow and give an idea of where there's kind of uncertainty in direction, where there's uncertainty in magnitude, where there's uncertainty in both. And so it gives you kind of a direct visual way of trying to encode that information.
So the longer glyph has more uncertainty in magnitude? Oh, it's the head of the arrow.
It's the head, yeah.
Just the head of the arrow,
Yeah.
okay.
And so this is kind of an intrinsic technique where you're changing your glyph to show the uncertainty as well as showing the other data set. So here's the same thing applied kind of on a flat 2D surface on a slice of a wind velocity. So this is, you know, with and without uncertainty. So this is building the uncertainty right into the texture simulation for doing a reaction diffusion texture. And so basically your little flow cockroaches get broader as the uncertainty increases and narrower as the uncertainty decreases. And so if you know directly which way they're going, they get skinny. If you don't, they get fatter, and it gives you an idea that you don't know which way they're going. And they're running towards their heads. And so this is basically showing on uncertainty in vector fields from particle imaging velocimetry. And this idea is not to show the uncertainty everywhere, but just to show the consequences of uncertainty as you kind of start from a particular location. And so they sieve the yellow flow and they kind of let it diffuse, and it gets more and more uncertain. In this one, it remains fairly certain in this one. So kind of the diffusion gives you an idea of where you might have gone. So this is showing error in vector fields, and so this is basically like line integral convolution, but instead of just doing integration along, it spreads the thing into a wedge, right? And so you can see that these wedges kind of have a large direction, and they're basically layered here, individual glyphs on top of each other enough that it looks like the line integral convolution, but each glyph has got this the uncertainty. Now, to me, this gives a very strong impression of kind of depth to this flow. It's like swirling away and down. And so this is caused by the occlusion effects and what seems to be perspective as these cones go down below. And so this is messing a little bit with our kind of perceptual machinery, but giving a pretty good understanding of which direction. I say pretty good because it seems good to me. Haven't done a user study to make sure, but you know, it gives an idea of the differences.
Has a weird sort of density property to it as
It's
well.
really
Yeah.
interesting, yeah. I could stare at it for hours. So this is basically positional uncertainty in molecules by overplotting, right? And so if you draw 1/10 the transparency version of the molecule 10 times at all the different locations, if it can't move, you'll get a solid one right in the middle. If it can move a lot, you'll get a blur near the edge. So this shows you which parts of the molecule are more likely to be stable and which parts of the molecule are more likely to be in motion. This is another approach of doing that. So it's basically showing you the probability density of the molecule as a volume rendering superimposed on the ball and stick model rendering of the molecule. All right, you can do a similar thing to the kind of probabilistic rendering by having things move, right? So you can imagine you have a lower error bar and an upper error bar. Well, you can have your surface just vibrate in animation between the lower one and the upper one, and that gives you an idea of the range. Sections of the surface that don't move, they're pretty certain. Sections that do move are quite uncertain. This is going to draw your attention to uncertain areas, which may be what you want if you're trying to see them, but it may have an unintended side effect of what they really care about are the parts of the surface that are certain. So then you can also do the same thing
Rainbow.
with vibrating color. Oh, you got me. Yes.
More truffles.
Yes. Slide 60. I was so careful with this one. Yeah, slide. All right. So here the surface doesn't change, but the color changes. It goes from red to green to rainbow, from green to rainbow to green to rainbow, and so it kind of flashes in the areas without changing the surface geometry to kind of highlight here's what's going on.
So the green is good and
So
the,
green is good, red is bad. I think green is probably average. Blue is probably good, and red is probably bad. That's normally the way the rainbow goes. All right. You can basically use line glyphs for showing uncertainty. Here, unfortunately, they picked isoluminate with the background line glyphs, and so I'm not sure you can see them. But what's drawn here are basically, here's the grid, and then here's a line for where this mesh point could be plus or minus, right? And they get bigger where there's more uncertainty, and they get smaller where there's less uncertainty.
If you move the structure in the opposite direction, then it is a good thing, right? Because the flat would be the normal, and previously it was like the error was moving the structure higher or lower, right? If you do it in the opposite direction, is it a good technique to use?
So here they were moving it up and down perpendicular to this, kind of along the ranges. But you're saying moving it sideways?
No. If the value is like flatly laid out flat,
Okay?
this structure was like, the error was like along the positive y direction, right?
That was where the uncertainty was in
Yeah, but if
this
you-
example, yeah?
But if you plot it along the negative direction,
You mean like sticks down from the surface to show where things are?
Yeah.
Yes. So you can, in fact, instead of animating the surface, just use these under a surface or above a surface, that's right. And it gives you an idea of the range where it could be. And so this is another line glyphs for doing. So the bottom plane is the mean elevation. The height field is the standard deviation. The contour color is the interquartile range, right? And so you can see the different ranges. And the line glyphs give you absolute difference between mean and median elevation values, right? So here they tried to pile everything onto the figure, and then I shrunk it down too small to get a good view here. So hopefully in the slides online you can zoom into this a little bit better, or you can look at the original image. So here they're trying to show the mean value at the bottom. The kind of height is the standard deviation, and so higher is more standard deviation. The contour colors give you the interquartile ranges, and the line glyphs are absolute difference between median and mean. Right?
so this is a visualization of the error,
Yep,
literally.
yep. So this is box glyphs for showing uncertainty. On the left, the height of the bar indicates uncertainty in the information. On the right, animated bars indicate uncertainty, and so they're kind of in motion there. They look blurred here in this particular frame of the image. Now, occlusion is going to be a problem with dense bar glyphs due to the oblique angles, right? So you're going to see the uncertain ones are going to hide the ones behind, but can't have everything. All right, so you can do the similar thing with points. So you can basically take every point on the surface and move it by a random amount within the probability distribution. And this basically explodes the locations, and you can't tell the surface where you shouldn't be able to tell the surface, but maintains nice, good shading where you couldn't tell the surface.
But it makes the surface look really weird.
It's the Kushi, what is it, Chia pet, right, visualization of what's going on. This, little problem, right? So here's uniform transparency, trying to show you the min, the max, the mean surface, and it all kind of blurs itself into a mishmash. So with kind of if you've done kind of a screen door transparency, had some texture on these, so you can see the upper, the middle, and the lower surface, then you would start to be able to get a better idea of what was going on. Or, as he suggested, if you put line glyphs above and below, they can give you an idea of what's going on. So this is very similar to the volume rendering we saw before, but instead of just making it uniformly transparent, it basically adds speckles in areas where there's uncertainty, and so things start to kind of disappear probabilistically along those regions. All right, so this is a 2D risk-based classification, and so this is basically showing you what kind of material each of these things is, and it delays the classification until rendering, right? So the importance is inversely proportional to the penalty for misclassifying. So if it's really important not to misclassify, then they keep make it harder to tell what's going on. So we're not going to classify here where it's where we're likely to get it wrong.
Okay.
So here's a volume rendering version of this, kind of low to high sensitivity. Where do we believe that the surface is right here, and where do we not believe that it's right here, depending on how sensitive it is to small changes in the threshold. You can have vibrating textures that basically which regions of this rock or which kinds of material can change from frame to frame to give you an idea that it might be this, it might be that, in a similar way that we saw the other.
So what's varying there? The lines moving around?
And so the texture that's filled in here would vary from frame to frame to give you an idea that you didn't know exactly what the material was over time. So color maps to indicate
Rainbow.
glyph uncertainty. Yeah. So, and so here's an extrinsic approach to kind of do the vector field as a vector field, and then the uncertainty as a color map on top. All right, so now we go crazy with glyphs. And so this is trying to understand what the radiosity error there was in this scene that's got a shark, a hammerhead shark, and a surfboard and some things on the wall. And we're drawing large spheres here to show where there's large error. So we get kind of a hard time understanding space, but we can see where there's large errors. This is using 2D circular textures on the left, so they get bigger when there's more uncertainty. And then there's 3D solid textures on the right, and so it just gets completely psychedelic to show you what's going on. This is surface patches translated in or out of their original positions to highlight differences, or rotated, right? And so this is kind of messing with the geometry in all kinds of ways, and with the color to show you different ones. And I kind of wanted to give you all these to give you kind of see different approaches. You can alter the diffuse coefficients according to the difference. And you can kind of speckled patterns where there's kind of incorrect countering, or you can alter the specular coefficients, and so it's very brightly shiny where there's problems and not so shiny where it's not. Now the one on the right depends on the viewing angle, so you're going to need to rotate the view around to get an idea of what's
Make it shiny, it looks smoother,
so
which
these
makes it more
two
accurate.
don't distort the surface the way as the others did, except they make it hard to see some parts of the surface, right? The fact that it's little squares doesn't confuse you that in fact it's a change in the surface shape. No, it's the tessellation of the surface. And this, again, if you rotate around, gets you kind of a change in the brightness of the surface.